Okay, today we will be talking about partial fractions, which, as you will see, is really a topic in algebra as much as calculus. We will be using partial fractions to integrate rational functions. What is a rational function? That doesn't mean a sensible function. The key here is ratio. A rational function is simply a ratio of polynomials, or if you like, a quotient of polynomials. So some examples would include any of these guys. In each case, we have a fraction where the numerator is a polynomial, and remember, a constant is a sort of degenerate polynomial, where the polynomial has degree 0, and the denominators are all polynomials. And we are going to be particularly interested in what I call bottom-heavy rational functions. These are the rational functions that have a denominator of greater degree than the numerator. So coming up to my 4 examples here, is the first one bottom-heavy? No, it is not, because the top and the bottom have the same degree. In a bottom-heavy rational function, the bottom has to have a strictly greater degree than the top. Okay, but when we look at our second example, we see this one is bottom heavy because its denominator is linear. It has degree 1. Its numerator is a constant, so it has degree 0. Our third example is definitely not bottom heavy. It's top heavy, in fact. The top has degree 2, the bottom has degree 1. But the fourth example is another bottom heavy rational function. The denominator has degree 2, whereas the numerator only has degree 1. Okay, so you know what a rational function is, and you know what a bottom-heavy rational function is. Why are we talking about them? We're talking about them because the goal for today will be to learn how to integrate at least certain rational functions. And it will turn out that the problem of integrating rational functions quickly reduces to the problem of integrating bottom-heavy rational functions. And you can understand why if you follow an analogy between rational functions and rational numbers. Recall that a rational number is just a ratio of integers, or any number that can be written in the form of a ratio of integers, such as any of these. And just as we spoke of bottom-heavy rational functions, we could speak of bottom-heavy rational numbers. These would just be fractions where the denominator is greater than the numerator. So in the 4 examples I wrote down here, a half, 1 over 2, is bottom-heavy, but 22 over 7 is not. That one is top-heavy. 3 over 14 is bottom-heavy. And in fact, 2 over 3 is bottom-heavy. Okay, fine. But who cares? Why are we going back to elementary school? I bring this all up to remind you of the fact that if we take a rational number that is not bottom-heavy, like this 22 over 7, we can take our not bottom-heavy fraction and rewrite it in such a way that we get the sum of 2 things, an integer plus a bottom-heavy rational number. So in this case, that would be, well, let's see, we just do the division. 7 goes into 22 3 times, but it leaves a remainder of 1. So we have 3 plus a 7th. Our top-heavy fraction becomes an integer plus a bottom-heavy fraction. And of course, we can do that with any fraction that is not bottom-heavy. 19/5, a top-heavy fraction, is going to turn out to be 3 plus 4/5. We took our top-heavy fraction and wrote it as the sum of an integer and a bottom-heavy fraction. So in some sense, we never have to deal with top-heavy fractions if we don't want to. We could always rewrite them as integers plus bottom-heavy fractions. And as many people will tell you who are not involved in mathematics in any way, they're more comfortable with such numbers. 19 over 5 sounds like a problem to be solved, whereas 3 4/5 is something very tangible. Anyway, I mention this stuff, as I said, because the exact same thing happens with rational functions and bottom-heavy rational functions. Namely, if you start with any rational function that isn't bottom-heavy, say, you can always rewrite it as a sum of 2 things. The first part is not going to be an integer. It's just going to be a polynomial, the sort of thing that goes on top and bottom of a rational function, just like an integer was the sort of thing that goes on top and bottom of a rational number. And the second term will be a bottom-heavy rational function. Just like with the fractions, our second term was a bottom-heavy rational number. But whereas you were perfectly comfortable writing 22 over 7 as 3 1/7, you did that long ago when you were still on your mother's knee, this kind of process might not be so familiar to you. But we actually obtain it in the exact same way. We just do it through division, albeit polynomial division in this case. I'll show you how it works. Let's take a rational function that is not bottom-heavy already. already. Let's use this one. X squared plus 1 over x minus 5. This is not bottom heavy, but my claim is that I can write it as the sum of a polynomial and a bottom heavy rational function. How will we do it? Simply through division. We will see, so to speak, how many times the bottom goes into the top, and then we will have a remainder, which of course will go over the bottom. But polynomial division is nasty and not something we do every day, so let me remind you down here in the dungeon how we do it. We will take our fraction and rewrite it as a long division problem. 8x squared plus 1 divided by x minus 5. You might recall that when you do things like this, it helps to keep your work straight if over here we actually leave a little space for the missing x term. We have an x squared term and a constant term. Let's just move the constant over like that. Okay, now remember how this works. We take the leading term over here, the one with the highest degree. That's going to be x. And we ask how many times it goes into the leading term here, which is 8x squared. Well, it's kind of a funny way of putting it. How many times does it go in? But what we're really asking is, what do I have to multiply x by to get 8x squared? Well, that, of course, is 8x. So I'm going to write that in the usual place in our long division problem. Is this stirring old dim memories? Well, let's see if you can remember what happens next. We have to multiply this 8x, not just by the x here, but by the entire denominator. And we write the result down here, and then we subtract, and then we repeat the procedure. So anyway, when we multiply 8x by x minus 5, what happens? Well, 8x times x, we said, is 8x squared, of course, but we're also multiplying 8x by minus 5, which gives us minus 40x. And this is why I left that little extra space there. It will make this subtraction easier. Okay, now we subtract this junk from what we had above, and that gives us, let's see, well, the 8x's cancel out, then I have nothing minus 40x, so I get a 40x, and then I have a 1 minus nothing, so I still have a plus 1. Okay, good. Am I done? No, not yet, because I have to see if my denominator goes into this new thing. Well, yes, it does, because what do I have to multiply x by to get 40x? Well, of course, that is 40, so I will put that up here. But when I put it up here, I have to multiply that 40 back by these guys, which gives me 40x, certainly, but also, because of this minus 5, minus 200. So when I do this next subtraction, I'm going to end up with the 40x's cancel out, but then I get 1 minus 200, which is 201. And now I have reached something whose degree is lower than my original denominator. So this thing is my remainder. And if I carry the results of this dreadful algorithm back over here, what it is telling me is that my original top-heavy rational function is going to be a certain polynomial, namely this one, so I'll put it over here, 8x plus 40, plus a certain bottom-heavy rational function. Well, that's like when we had 22 over 7, and we said that's 3 plus 1/7. Analogously, this bottom-heavy rational function is going to have a denominator equal to the original denominator, namely x minus 5. What goes upstairs? Well, it has to be something whose degree is lower than the degree of the denominator. So it has to be degree 0, a constant. What constant will that be? Well, of course, that is our remainder, which is 201. And lo and behold, we have done it. We took our original top-heavy rational function and rewrote it as the sum of a polynomial and a bottom-heavy rational function, using nothing more than good old-fashioned polynomial division. Okay, but why would we want to do that? We want to do that because if we're trying to integrate a rational function that is not already bottom-heavy, that polynomial division trick rewrites it as a sum of two simpler functions. And since the integral of a sum is the sum of two integrals, we like that. It makes life easier because integrating a polynomial is, of course, utterly trivial. And now all we have to worry about is integrating bottom-heavy rational functions, which are simpler. And this justifies my statement earlier that the problem of integrating rational functions in general really just reduces to the problem of integrating bottom-heavy rational functions. So we will start on that particular problem in a moment. In fact, let's begin with the simplest bottom-heavy fraction of them all, 1 over x, the reciprocal function. What do we get if we integrate it? Now, we've seen this before, and we have said, oh, that's just the logarithm of x. And that's that, right? Well, that's sort of right. This is really only half of the story. And at this point, I'm sure you're ready to say, what are you talking about? It's only half the story. Obviously, this is an antiderivative of 1 over x. Everybody knows that if you take the derivative of this, you get 1 over x. That's the whole damn story, right? Well, let's think about these two functions, the logarithm function and the reciprocal function. There's a very important distinction between them. Think about their graphs. Start with the function that we want to integrate, the reciprocal function. What does its graph look like? Well, you all know what that looks like. It's not defined at 0, and it has these two branches, one for positive values of x and the other for negative values. But the important thing is that this function is defined for all non-zero values of x. So, of course, a true antiderivative of the reciprocal function should also be defined for all non-zero values of x, right? Oh, you see the problem. What's the domain of the logarithm function? It is not all non-zero real numbers. The natural logarithm is defined only for positive values of x. And that is why I say that this is only half of the story. If we're just talking about this reciprocal function for positive values of x, then it's the full story. But if we're allowing x to be negative as well, what's the antiderivative over there? Knowing that is going to be very important for us when we integrate bigger rational functions than this one. So let's complete our story. Oh, actually, before we complete the story, I just want to be completely sure that you understand why the logarithm function is only defined for positive numbers. Why, for example, is the logarithm of -3 undefined? I mean, you know, for example, why the square root of -3 is undefined, because this would be a number whose square is -3. And of course, when you square any real number, you get something positive, or 0, but you never get anything negative. So this thing is undefined. But what about the logarithm of -3? Well, again, what would that even mean? This would mean the power that you have to raise e to get -3. Is there any such power? Well, of course there isn't. Think of the graph of the exponential function. No matter what you put in, e to the anything is always positive. You can't raise e to some real power and get -3. So this is also undefined. And of course, there's nothing special about -3 that holds for the log of any negative number. All right, end of digression. Back to the question at hand. What is the full antiderivative, the full story of the integral of 1 over x? Well, let's talk about a function that is very similar to the log of x, namely the log of the absolute value of x. This function is obviously defined for all positive numbers. It's just the ordinary logarithm, but it's also defined for all negative real numbers, because if we pop -3 in for x, well, we get the logarithm of the absolute value of -3, which is the logarithm of 3, which is a perfectly good expression. And if we wanted to write this out more carefully, we could say that the logarithm of the absolute value of x is defined piecewise. It's just equal to the log of x when x is positive. Obviously, if you throw 5 into this function, you get log of absolute value of 5, which is the same thing as log of 5. But when x is negative, when you pop x in here, the absolute values will change its sign. So instead of taking the logarithm of that number x, which is negative, you'd be taking the logarithm of the opposite of that number x, which would be positive. So now we've specified exactly what it is the logarithm of the absolute value does on its two branches. And in fact, if we were to graph this function, what would it look like? Well, for positive values of x, of course, it stays the exact same. But what happens when I put in negative values of x? Well, then I'm graphing log of -x, which looks exactly like this one. But when I substitute -x for x in an equation, remember what that does to its graph. It reflects it over the vertical axis. So this part of the graph of this function would look like this. And just as we say that collectively these two branches of this hyperbola make up the graph of y equals 1 over x, we could say that collectively these two branches of this function collectively make up the graph of y equals the logarithm of the absolute value of x. Now the only question is this in fact the full antiderivative of the reciprocal function? Only one way to find out. Let's take its derivative. So if we're taking the derivative of the log of the absolute value of x? Well, we just have to think about what happens on each of its branches. That's going to be the derivative of log x when x is positive, and the derivative of log of minus x when x is negative. Well, the derivative of log x for positive values of x, we know is just 1 over x. So that holds when x is positive. For the second branch, the derivative of log of minus x. Well, we need the chain rule for that. We get 1 over minus x because of the logarithm, but then we have to take the derivative of the inner function, which is minus 1. Oh, but when we multiply those together, we get plain old 1 over x. And this holds when x is negative. So the derivative of the log of absolute value of x is 1 over x when x is positive, and 1 over x when x is negative. So I don't need this piecewise defined function anymore. I could just say that it is equal to 1 over x for all non-zero x. Aha! So we have indeed found a function defined for all non-zero x whose derivative is 1 over x for all non-zero x. So although the statement we'd been using so far was only half the story, now we can fill in the complete story. The integral of the reciprocal function is the log of the absolute value of x plus a constant for all non-zero x. And that is the complete story of the integral of 1 over x. And we will use this fact from now on. Good. In fact, let me box this up and move it into the corner. Just hang it on the wall so we remember what we have accomplished. Okay, now with the simplest bottom-heavy rational function disposed of, we can take care of an entire class of bottom-heavy rational functions very easily. Namely, if we want to integrate a rational function, a bottom-heavy rational function, where the bottom is a linear polynomial, in other words, degree 1, then the top would have to be, if it's going to be bottom-heavy, this has to be a lower degree, so this would have to be a constant function. Those are the only degree 0 functions. We can now integrate anything of this form very, very easily. For a specific example, let's integrate, let's do something over 4x plus 7, and the top has to be a constant, so why not make it 5? How can we integrate something like this? Well, it's a piece of cake, because first of all, I have this constant multiple, 5, so I can bring it through the integral sign. Like so. Now we need to integrate 1 over the quantity 4x plus 7. Well, look, that's 1 over some quantity. It's basically a reciprocal function. So we can just play the guess and adjust game and come up with the antiderivative of that, right? I mean, we bring the 5 along, and then what's an antiderivative going to be? Well, we said this is like 1 over something, kind of 1 over u. So this should be something like the log of the absolute value of u. So let's just try the log of the absolute value of 4x plus 7, and we'll make adjustments as needed. Does that do the job? Well, if I take the derivative of this stuff, I know I get, when I take the derivative of the log of absolute value function, I get 1 over that thing. So I'm going to get 1 over 4x plus 7. Ooh, but then the chain rule tells me I get an extra 4, and I don't want a 4. I just want the 1 over 4x plus 7. So I need something to balance out that 4. Well, that is easy. Of course, I just insert a 1 over 4 there. And of course, this will look nicer if instead of having 5 times a quarter and these extra parentheses, I rewrote it all as 5/4 times log of absolute value of 4x plus 7. And of course, our magic constant of integration. And that's that. And I hope you see there was nothing special about the 5, the 4, or the 7 here. This way of thinking would get you the integral of anything of this form. You just pull the constant through the integral, and then you're integrating 1 over something very simple, and the guess and adjust game will take you the rest of the way. Maybe one more very quickly. Let's integrate pi over ex plus the square root of 2. Well, of course, we can pull the constant factor of pi through the integral, like so. And now, to actually do this integral, we just think, well, this is 1 over something. So we kind of expect to get something like log of the absolute value, don't forget the absolute value, ex plus root 2. But is the derivative of this stuff equal to the integrand here? Well, we know when we take the derivative of this function, this log absolute value function, we get 1 over the stuff in absolute value, which we want, but the chain rule tells us we're also going to get a factor of e, which we don't want. So to balance that out, I have to put a 1 over e in here, because when I take the derivative of all this stuff in the parentheses, the 1 over e just sits there, and the derivative of this is going to be e times this stuff. And that e will cancel with the 1 over e and leave me with the thing I am aiming at. And of course, pi times 1 over e is pi over e, and don't forget to put the cherry on top. And that's that. Now you see how to integrate any bottom-heavy rational function where the bottom is linear. linear. We've already made a lot of progress, but we're going to push it further. Oh, actually, before we push it further, let me do one more example of this sort. Hey, wait a second, you might say. This is not an example of this sort. Look, you fool, the top is not a constant like it's supposed to be. It's linear. True, but I can turn this into something of this sort. Because what's the first thing we should check? Is this rational function bottom heavy? No, it is not. The bottom and top have the same degree. So what can I do here? Well, I could carry out the polynomial division, which is not really a task I relish, but if we did it, we could turn this into a polynomial plus an integral of this form. But I want to take this opportunity to show you a little algebraic trick that sometimes works. There are a million tricks associated with the algebra we are studying in this particular section, and I don't want to bore you with all of it, but sometimes you can make your life a little easier by not plodding along the usual path. So if I were faced with this, rather than doing the polynomial division, what I would do is say, hey, I can actually make this work in a simpler way. Here's a neat trick. I'm going to take the numerator of that fraction, and I'm going to rewrite it in a nicer form. Instead of putting 5x plus 1, I'm going to write it as 5x minus 3 plus 4. What? Why would I do that? I mean, sure, it's the same thing because minus 3 plus 4 is 1, but why would I want to? Only because I'm thinking one step ahead here algebraically. I could break this thing into the sum of two fractions right away. This stuff over 5x minus 3 plus the 4 over 5x minus 3. That's just ordinary arithmetic of fractions, right? And though I probably don't need to write this out in 2 steps, I will. There's the first one, but the second one is the whole reason I set this up. What's 5x minus 3 over 5x minus 3? It's 1. And lo and behold, look what I've done. I accomplished exactly what polynomial division would accomplish. I rewrote this original junk as the sum of a polynomial, a real simple polynomial, and a bottom-heavy fraction. And now that's easy to integrate. An antiderivative of 1 is x. An antiderivative of this one, well, let's see. I'm just going to try to write it all down at once. Pull the 4 out, and we're just integrating 1 over 5x minus 3. Let's see, so it's going to be something like log of 5x minus 3 in absolute value. When I take the derivative of that, I get 1 over 5x minus 3. Ooh, but I get a 5, so I have to balance that out with a fifth. The 4 and the fifth combine into 4/5, tack on the constant, and we're done. Anyway, that's a neat little algebraic trick that sometimes you can use. Okay, and after all that, now it is finally time to discuss partial fractions. This is an algebraic topic concerning rational functions, and in a complete treatment, we would need to consider a number of different cases. I am mostly going to just concentrate on the first case, which is the most common one. I will say a few words about the other cases at the end of the video. So, if we have a bottom-heavy rational function whose denominator can be expressed as a product of distinct linear factors, then it is possible to rewrite the rational function as a sum of simpler bottom-heavy rational functions whose denominators are the distinct linear factors of the original function. And this sum is called a partial fraction decomposition of the original rational function. Phew! All right, I realize that is quite a mouthful, but an example will make the idea clear. So let's look at this bottom-heavy rational function. This crazy statement up here applies if the denominator can be expressed as a product of distinct linear factors. Well, is that the case here? It is, because the denominator here can be factored like this. And we have 2 linear factors here downstairs, and of course they are not the same thing, so they are distinct. So what does this stuff tell us? It tells us that it should be possible to rewrite this rational function as a sum of simpler bottom-heavy rational functions whose denominators are these 2 distinct linear factors. In other words, I should be able to write that this stuff is equal to something over x plus 2, the first factor, plus something else over 2x minus 1, the second linear factor of the denominator. And if we can figure out what these numerators were, we would have a partial fraction decomposition of our original rational function. And all of this you can think of as a particular theorem telling us that under the given conditions, such a partial fraction decomposition always exists. It doesn't tell you what these numerators must be, but we can figure that out on our own. In fact, there's one thing we know already. These terms in the partial fraction decomposition are themselves going to be bottom-heavy rational functions. But since the bottoms are linear polynomials, the tops have to be constants. Otherwise, they won't be bottom-heavy. So instead of these question marks, let's just put a and b, where a and b are some constants. Now, how can I figure out what a and b actually are? Sometimes you can just stare at this thing for a little while and do some mental calculations, and you might be able to come up with it. But we are not always so lucky, so we do need some more systematic way to approach the problem. So for determining a and b, let's try this. First, clear the fractions. In other words, let's multiply both sides of this equation by an appropriate factor to get rid of all the fractions. That factor, of course, will be the denominator of the original fraction. Doing so yields, well, what do we get? When we multiply this side by the denominator, of course, we just get the numerator, 3x plus 5. But when we multiply this side by the denominator, we get a times 2x minus 1 plus b times x plus 2. And of course, this original equation holds for all values of x for which it is defined, which means that this equation also holds for all values of x. And I'll use that fact in a moment. From this equation, there are a few different ways that we can figure out what a and b have to be. I will show you two such ways. The first is more tedious, but it gives us some useful information really in any situation like this. And that first way would be simply to expand everything out here and write it as a single linear expression, and then equate its coefficients with the coefficients over here. If we were to do that here, this stuff on the right would become 2a plus b x plus the constant 2b minus a. That is just very basic algebra. And since that is equal to this stuff, which is equal to 3x plus 5, equating the coefficients on the two sides tells us that, well, let's see, the coefficients of the x terms must be equal. So we would have that 3 is equal to 2a plus b, and the constant terms must be equal. So the constant on the left, 5, must be equal to the constant on the right, 2b minus a. And thus we have that 5 must equal minus a plus 2b. And now we have this little system of linear equations. And if you solve that little system of linear equations, you will discover, as you should verify, that a is 1/5 and b is 13/5. So if we substitute those values back into our original expression, we would see that our original bottom-heavy rational function can be decomposed into partial fractions in this way. 1/5 over x plus 2 plus 13/5 over 2x minus 1. And you should see how this will ultimately help us in integration. If we had to integrate this rational function right here, we might have some trouble at first. However, if we rewrite it, do a partial fraction decomposition in this form, that is really easy to integrate because we do it term by term, and each one of those terms is of a form we already know how to integrate, as we discussed before, because each one is a bottom-heavy rational function with a linear function downstairs. But I'm getting ahead of myself. We haven't seen any integrals yet, but so far, I hope you understand this idea. And you might be thinking, well, that's really tedious. And you know what? I agree with you. I want to show you a simpler way that will work sometimes, and in fact will always work in the case we're looking at right here. So let me rewind the tape a little bit. And we are back to where we were a moment ago. Our result up here told us that we could decompose this bottom-heavy rational function, whose denominator is a product of distinct linear factors, into this particular form. And we were trying to figure out what a and b are. I showed you one way to do it, but I'll show you a nicer way. We still begin by clearing the fractions, and we end up with this linear equation right here, which holds for all values of x. Well, rather than equating the coefficients, which certainly worked, let's see if we can just think of some particular values of x that will help us figure out what a and b are fairly directly. For example, when x is minus 2, this equation becomes, well, let's see, when I pop minus 2 in the left-hand side, I get minus 1, And when I pop minus 2 into the right-hand side, what happens? This term vanishes because I get minus 2 plus 2, which is 0. And that, in fact, is why I chose to use x minus 2. So that very conveniently vanishes. And this piece becomes minus 5a. Hey, look at that. I've got a really simple equation. And if I solve it for a, I find that a is a fifth, just like we found before. Good. Well, if I wanted to, I could feed that back into the original equation and maybe then equate coefficients or whatever. But let's do it in an easier way. Is there some other value of x that will help us figure out what b is? How about a value of x that will make this whole term disappear so that b will be the only mystery constant left? What value of x will work there? Of course, it's going to be whatever makes this 0, and that is going to occur when x is half. When that happens, this equation becomes, well, when I pop half into the left-hand side, I end up with 3 halves plus 5. 5 is 10 halves, so that's going to be 13 halves. And when I pop half into the right side of the equation, this first term vanishes, and the second term becomes 2.5b, better known as 5 halves b. Solve for b, and we get, once again, that b is 13 fifths, just like we found in the first method. Do you like that second method better? I'll bet you do. I certainly do at any rate. So now that we've found a and b, once again, we could stick them in our original decomposition, which we could then use to integrate the original function. In fact, let's go ahead and do that. The integral of this original rational function is something we could find by doing this partial fraction decomposition, which now becomes a really easy integral. Integrating the first term, we get, well, the fifth just sits there, and the integral of 1 over x plus 2 is going to be log of the absolute value of x plus 2, and we don't need anything to balance because the chain rule doesn't give us anything extra here. Plus, well, let's move on and integrate the second term. Once again, the 13 fifths can be pulled through, and what we're really integrating is just plain old 1 over 2x minus 1, and we can get that through a guess and adjust. Its integral is going to be not quite log of absolute value of 2x minus 1, because if we take the derivative of this guy, we get 1 over 2x minus 1, but we also get a 2. So I need to balance that with a half. And of course, let's combine our fractions there. That'll give us 13 over 10. And don't forget the constant. And that's that. And congratulations, you have just done your first integral by partial fraction decomposition. It looked simple on this one line, but crossing that first equal sign was a little tricky because we had to do that partial fraction decomposition, which involved a fair amount of algebra. I believe I told you a while back that if you asked any calculus student for their favorite integration technique, they would probably tell you substitution. Well, I must admit that if you then asked them what was their least favorite integration technique, they would probably tell you integration by partial fractions because it is so algebraically tedious. Now, there is some interesting algebra. For example, this stuff that I just described as case 1 is a little algebraic theorem. Why is this true? I made this assertion here and then I just used it, but is it even true? It is, but proving it is tedious, so I am not going to bother doing that here. Otherwise, this video will never come to an end. Speaking of which, we should move on and do one more example of this sort of thing. Let's try to integrate this appalling rational function. Oof, buckle up. Well, the first thing we should notice is that we don't like this one bit because it is not a bottom-heavy fraction. We like bottom-heavy rational functions. So what can we do to fix that? Of course, we can do the polynomial division. The details are very boring, but when all the dust settles, you should be able to rewrite the integrand like this. Now, recall why we like that. We can do integrals term by term. This term is easy to integrate because it's a polynomial, and this one is not so bad because at least it is a bottom-heavy rational function. So that is going to be, well, let's see, when we integrate the first term, the polynomial term, we get this stuff, x cubed over 3 plus x squared over 2 plus x, but we still have to integrate the bottom-heavy rational function in the second term. How are we going to do that? Ooh, will substitution help maybe? I mean, the derivative of this thing is quadratic, but no, it doesn't work out right. Oi, are we stuck with a partial fraction decomposition? Well, can we even do a partial fraction decomposition? Does this thing factor into distinct linear factors? It does. Of course, you can begin by factoring out a x, and then noticing what remains is a difference of squares, so it becomes x minus 2 times x plus 2. And yes, indeed, these are three distinct linear factors. So our little theorem on partial fraction decomposition applies. Now, that means that we should be able to write this thing as a sum of three fractions whose denominators are x, x minus 2, and x plus 2, and whose numerators, of course, are just going to be some constants, which we will call a, b, and c. We're going to keep all the scratch work over here to get it out of the way. Anyway, when we clear the fractions, this becomes all of this junk, which is so ugly that I can't even fit it on one line. Now, how do we proceed from here? One thing we could do is recognize that this stuff is all a quadratic, all expanded out. If we multiply this stuff out together, we could just write it as a single quadratic, equate the various coefficients. That would lead us to a system of three linear equations and three unknowns, where the unknowns are a, b, and c. Solve that system, and we would have our values of a, b, and c. But I know you like the other way better, because you are men and women of taste. So let's do that. This equation we know holds for all values of x. So in particular, when x is, what's a good choice to consider? Well, we want something that is going to kill a couple of terms of this right-hand side. Hey, let's use x equals 0. That'll knock out that term and that term as well. So when x equals 0, this becomes what? When x is 0, the left-hand side, of course, just becomes minus 20. As for the right-hand side, well, when x is 0, that is going to kill the third and second terms, because they both have an x in them, and all that remains is the first one. When x is 0, we get minus 2 times 2, which is minus 4 times a. Thus, a must be 5. Good. When x equals 2, another wise choice, because it will make 2 of the terms on the right vanish, we get, well, let's see, when we pop 2 in there, we get 32, and when we do the same thing on the right side, the outer terms vanish, and all that's left is the inner one, so we get 2 times 4, which is going to give us 8b, so b must be 4. And finally, when x is minus 2, and we make that choice to kill the first term and the second term, when x is minus 2, the left side becomes minus 24, while the right side becomes, well, let's see, this is the only term that survives, so we get minus 2 times minus 4, that is going to be 8c, so c is minus 3. Anyway, we have found what we were after, which means that I can rewrite this integral by doing our partial fraction decomposition. So this whole thing becomes this stuff. I've just taken my values of a, b, and c, substituted them in here, and then substituted the partial fraction decomposition for the entire expression. And now this is a straightforward integral. First term, integrate it, and we get 5 log x. Second term, integrate it, and we get 4 times log of x minus 2. Last term, integrate it, and we get minus 3 log absolute value of x plus 2. And of course, the constant of integration. And at long last, we have our antiderivative. If we took the derivative of all that junk, we would get our original integrand. And you know, we could actually combine these terms using some properties of logarithms, but I'm going to be naughty and just let them sit as they stand. Well, what the hell, very quickly. This term, of course, can be rewritten as log of absolute value of x to the 5th power, right? It's just using that basic property of logarithm. Exponents get pulled down, or in this case, I'm pushing it back up. And in fact, think about what that means. Absolute value of x to the 5th power. That's this, right? Well, forget about the logarithm for a second. Think about absolute values, properties of absolute values. The absolute value of a product is the product of the absolute values. Or read that backwards. The product of the absolute values is the absolute value of their product. But you multiply x by itself 5 times and you get x to the 5th. And now we clearly don't need those parentheses outside the whole thing. And this is a bit too spacious, so let's patch that up. That looks better. And we can do similar things with these terms. The second term, for example, becomes this after the same kind of shenanigans with the logarithm properties and absolute value properties. And this term becomes this stuff. Now, what was the point of getting those coefficients out of the way? It was that now we can use other properties of logarithms. The sum of two logarithms, we know, is the logarithm of their product. Well, the product of two absolute values is the absolute value of the product. And now I don't need those parentheses anymore, since the absolute values function as grouping symbols. But bring that term down, and now we can use the fact that the difference of two logarithms is the logarithm of their quotient. Well, the quotient of two absolute values is the absolute value of the quotient. Now these parentheses have become redundant again, and look what we have achieved. We have combined all three of these terms into one. So if we really wanted to, we could rewrite this entire expression as our polynomial part plus the logarithm of this horror show plus a constant. Either way, whether you write it like this or like this, it's disgusting. But you should, of course, understand how to manipulate logarithms and absolute values, even if you keep it at this stage. Let it be that you keep it at that stage because you find this equally disgusting and not because you are actually unable to do that. If you're unable to do it, maybe it's worth practicing. All right, we have reached the end of example 2, and integration by partial fractions, I regret to tell you, can be even more horrifying than this. So much so, in fact, that in practice, if the problems get much nastier than this, realistically, most people are going to turn to a computer to do the integral for them. And it is for this reason that in the book I commit the minor heresy of not going much deeper into partial fractions than what I have done so far here. Still, it is worth knowing of a couple little twists on the technique of partial fractions and how you can handle them if you ever must. So, a while back I described what I called case 1 of partial fractions, where we had distinct linear factors in the denominator, and we have more or less completely handled that case. But what if either of these two conditions are not met? Like, for example, what if we have linear factors in the denominator, but they are not all distinct? What if we have some repeated linear factors in the denominator? What then? For example, consider this rational function. It is bottom heavy because if we square that out, this becomes a quadratic multiplied by x, and we have a cubic downstairs, but only quadratic upstairs. So we're happy about that. But can we do a partial fraction decomposition here? The problem is this repeated linear factor. We do not have distinct linear factors in the denominator. We have x, which is fine, but then we have x minus 1 and then a second copy of x minus 1. And it's natural to ask, well, what's so hard about that? I mean, surely we can just treat these as two separate factors and break this up into three pieces, one for each linear factor, like this, right? Each factor of x minus 1 gets its own fraction. Why won't that work? Well, it's not too hard to see why that won't work. Just do the arithmetic. Bring the first term down, and then these get combined because they already have a common denominator into b plus c over x minus 1. And then when we add these two fractions, we get all this stuff. Do you see the problem? This is supposed to be equal to our original rational function, but that's impossible. If nothing else, look, the denominator over here is a quadratic, whereas over here it is a cubic. So clearly that does not work. Similarly, the numerator over here is linear, whereas it is supposed to be quadratic. So the moral of the story is that as tempting as it might be to break our original up into three fractions of this form, it doesn't work. There is no way to choose constants a, b, and c to make that happen. However, there is a little twist we can make so that something very like this will work. The only difference is in this third term. Instead of having our constant over x minus 1, a second copy of the x minus 1, we put it over x minus 1 squared. And now, if we go through the usual algebraic contortions, clearing the fractions and so forth, we can actually find constants a, b, and c that will make this work, as you can see if you take the time to write it all out yourself. Okay, so we feel a little more comfortable about repeated linear factors. So can I get rid of those three question marks? Well, let me get rid of two of them for now, because you might say, well, okay, that's what happened if I had a squared linear factor. But what if we changed the original fraction a little bit? What if we had three copies of the linear factor x minus 1 in the denominator? How would that change the partial fractions decomposition? Is there still one? There is. Naturally, we will still have a fraction with x in the denominator and some mystery constant upstairs. But what do we get over here to account for our three copies of x minus 1? Well, we know it's not going to be something like this. The way we patch this up is something you might guess already. What we do is to keep three terms, but one of them will have x minus 1 downstairs. The other will have x minus 1 squared downstairs. And the last one will have x minus 1 cubed downstairs. And if we start with a guess, so to speak, of this form with these unknown constants a, b, c, and d, the usual algebraic shenanigans of clearing the fractions, picking certain values of x to make things work, or equating the coefficients, whatever you want to do, those usual moves will work, and you will be able to find constants that make this equality true. And thus, if you wanted to integrate something of this form, you could do it by partial fraction decomposition. Crack it into a sum of 4 integrals, each of which is easy, right? Because this would be a log x, and this would be b log x minus 1. These would be a little more subtle, but not much, because these are things of the form roughly, after you pull the constant out, 1 over u squared, and this is something like 1 over u cubed. So they are really just power functions in disguise, u to the minus 2, u to the minus 3, and you can integrate them. Well, you understand how it works. If we had, instead of a third power, a fourth power, of course, we would need a fourth term on there. And if the denominator had, say, multiple repeated linear factors, like the square of x minus 1 and the cube of 2x plus 1, we could do the partial fractions decomposition, but we would end up with 5 little fractions on the other side. It would look like this. Because we have 2 factors of x minus 1, we get one term over here with an x minus 1 denominator, and another one with an x minus 1 squared. Because we have 3 factors of 2x plus 1, we get one term over here with a 2x plus 1 denominator, another one with a 2x plus 1 squared denominator, and a third with a 2x plus 1 cubed denominator. And from here, everything is set up for you to go to town, algebraically speaking, clear the fractions, equate the coefficients, and figure out what the values of a, b, c, d, and e must be. And at this point, I'm ready to erase that last question mark and say, you understand what is involved in that case as well. So is that it? I mean, factors are either distinct or repeated. There's no other options, right? Well, that's true, but they don't necessarily have to be linear, now do they? Oh, drat, because not every polynomial can be factored into linear factors. Many can, but not all. For example, suppose you ended up with something like this. I've got a bottom-heavy rational function, degree 3 downstairs and 1 upstairs, but this is as much as we can factor the denominator. I've got one linear factor, but this quadratic here cannot be factored any further, at least not over the real numbers. So we would call this guy an irreducible quadratic. Well, that frustrates both of these cases we've considered already. What are we to do in this case? Is partial fractions not going to work? Well, it'll work, but there's something else you have to do once again, which I'll point out very quickly, just so you've seen it. And if, under some bizarre set of circumstances, you are trapped on a desert island somewhere and can't get off until you can integrate something like this, you'll know how to do it. Well, we begin as you'd expect. One term in the partial fraction decomposition is going to have as its denominator the linear factor, 3x minus 4, and some mystery constant to be determined later will be its numerator. And then we will have another term whose denominator is, in fact, the irreducible quadratic x squared plus 1, but, this is the interesting twist. The numerator is no longer going to be a constant. Because of this irreducible quadratic here, which is degree 2, we have to put a degree 1 polynomial as a possibility up here. So it's going to be something of the form bx plus c, where the b and c are unknown constants. Now, it might turn out that b is 0, in which case this really is just a constant, but it might not. But anyway, once you have something like this, you are good to go. Bring on the algebra, and you can figure out what a, b, and c must be. And we like that sort of thing because although this might look intimidating if we wanted to integrate it, once we have cracked it open into a form like this, and we can break it into 2 separate integrals, well, this one's really easy. That's the kind we talked about at the beginning of this video. And this one's not much harder because to integrate something like that, well, we could take this term and cut it into a sum of 2 simpler expressions. And each one of those is easy to integrate. The second one, of course, is basically going to be an arctangent. In fact, it will be c arctangent x. And this first one is not hard. That one looks like a job for substitution. Good. So we know how to handle the presence of an irreducible quadratic. Oh, but I said an irreducible quadratic. Oh no! What if we have repeated factors of an irreducible quadratic in the denominator? Like, what if that x squared plus 1 factor shows up 3 different times? Well, I'll bet you can guess how we handle that. To supplement this term, we're going to need two more. One with the square of x squared plus 1 in the denominator, and one with the cube of x squared plus 1 in the denominator. And the numerators are still going to look like the form of the original one, namely linear functions. Like maybe this one will be dx plus e for some constants d and e, and the last one might be something like fx plus g for some constants f and g. And once we have set up everything in this form, you are all set up for a dreary algebraic task. And after working out the details, you will figure out what those various constants must be, so that if you need to integrate this guy, you can reduce that to integrating each one of these four terms, which are much easier to handle. So now you know how to cope with irreducible quadratic factors, distinct or repeated, in the denominator. You will be happy to know, I think, that a deep result in algebra tells us that any polynomial whatsoever, so any possible denominator of a rational function, can, at least in theory, though it might be difficult in practice, be factored into linear and quadratic factors. So I don't have to add another bullet point for irreducible cubic factors or anything. Such things, mercifully, do not exist. But that, my friends, is partial fraction decomposition in a nutshell. Kind of interesting in its own algebraic way, but tedious to carry out in practice. And that is about it for integration by partial fractions, everyone's least favorite integration technique. Next time, we will be doing some integrals using some trigonometric trickery, which is considerably more fun, at least if you are comfortable with trigonometry, which you should be. If you are not, review it. You'll be using it very soon. And what else? My time is running out. The video is ending when this thing disappears. Goodbye.